Section 21.4, Rates of Radioactive Decay. So radioactive decay is a first-order process. Okay, so if you remember from kinetics, a first-order process has something characteristic called a half-life. And a half-life usually looks something like a J-curve. And it's really just the time required for half of any given quantity of a substance to react. So at a certain amount of time, let's say I take a time from here to here, we're going to see the half of the stuff's gone. Half of it's reacted. In the same amount of time, the next element of time, another half has reacted. And in the same amount of time, another half is reacted. So in a half-life, whatever a half-life is, one half of that stuff is gone. If you take the same amount of half-life, let's say a half-life is 1 day. If after 24 hours or 1 day, half of the material is gone. If you wait another whole day, half of the remaining is gone. Okay, so half of the half is now gone. If you wait another day, half of the half is gone. So that's why it's a J curve down. It takes one time element to go half of the remaining amount, and it goes down with a limit towards 0. Okay, so the K is called the decay constant. Okay, it's just like any first order reaction. And what you'll see in terms of use of reaction is the N. Okay, so the N is the number of radioactive nuclei in the sample. So you have the original number of nuclei is n to the 0, and the number at whatever time that you're talking about is n to the t. So if you were to start with a certain amount, n to the 0 amount of radioactive nuclei, and then at time t, if you add half of that amount, okay, then you know that you're at 1 half-life. And so the ln, that's the natural log. It's a button on your calculator. The natural log of the amount of radioactive nuclei at whatever time you're talking about divided by what you started with is going to be equal to negative kT, and that K, okay, that's how you're solving for K, is called the decay constant. So how fast is it decaying? You're going to have some radioisotopes that will decay in a millionth of a second. You have other radioisotopes like uranium-238 that takes eons to break down. It takes thousands of years for half of it to go away. So that is this is pretty useful. But the main thing I want you to remember is this idea of the half-life. So if you do the calculus with that natural log, you'll end up with the time of the half-life is going to equal 0.693, it's another constant to remember, divided by whatever the K is of that particular stuff. And every stuff has a different K. So comparing the amount of radioactive nuclei present at any given time with the amount normally present, you can find the age, that's the T, half-life age of any object.